Welcome back to the video lecture series for Introduction to the Art of Programming using Scala. In this video we're going to talk about the third and last of the sorts that we're going to cover in this chapter. We're going to look at insertion sort. So we've already looked at bubble sort and selection sort. And we've talked about the fact that bubble sort, while it's very easy to code, it's not really something that you would do in real life because it involves lots of swapping around. The selection sort is something that you might actually do, especially if you have items where moving an item is costly. Something like the moving cars in a parking lot, maybe even moving weights in a gym. But if you were doing something with small items that were easier to move, you might not be tempted to use a selection sort. In that case, you might actually decide to use an insertion sort. So if we go back to our standard array that we've been playing with, and we look at what happens with an insertion sort. The idea of an insertion sort is we're basically going to, at any given time, ignore the back end of the array. And so we're going to start off with effectively thinking of this as an array of two elements. And we're going to look at the last element in it and ask the question, is it in the right place? Okay, in other words, does it go before the 5? And as we do this, we wind up building up a larger and larger array in the front that is perfectly sorted. And so every time that we insert something, we only have to move it as far forward as it needs to go. And we'll see that's actually a significant advantage to the insertion sort. So let's go through and look at what insertion sort would do with this particular array. So we, once again, if an array of one element, just the 5, is sorted, so we don't even bother dealing with that, we start by looking at the 8. And we ask the question, does the 8 go before the 5? And the answer is no, so nothing changes. Does the 3 go before the 8? The answer is yes. Now, instead of doing swaps, so you can write an insertion sort that does swaps. However, because of the way that the insertion sort works, it's actually far more efficient if you take the item that you're going to be working with and you store it down here in the temporary. And then I look and I say, does 3 go before the 8? And the answer is yes. So we simply drag the 8 back. We copy it back. Does the 3 go before the 5? Yes. So the 5 moves. Notice that I pulled the 3 down, and then I moved the 8 and the 5, and then I pull the 3 back up. Whereas otherwise I would have done 1, 2 swaps, and every swap has to do a total of 3 assignments. So I would have 6 assignments there instead of the 1, 2, 3, 4. And that advantage will actually grow as we go on. So for example, the 2. Well, I'm going to pull the 2 down, and then I check, does 2 go before the 8? Yes. So I pull this back. Does the 2 go before the 5? Yes. So I pull this back. Does 2 go before the 3? Yes. So I pull this back. And here is the 2. The 9. And this is where insertion sort can get a big advantage. So at this point, I know everything 8 and forward is sorted. So I look at the 9 and I check, does the 9 go before the 8? And the answer is no. So I don't do anything, and now I know that it's sorted out to here. What about the 6? Well, the 6 does go before the 9, so we'll pull it down here. We pull the 9 back. We pull the 8 back. And then I copy the 6 back up into here. With the 4, take the 4 down, pull the 9 back, pull the 8 back, 6 goes back, 5 goes back, and the 4 gets copied into location right there. Now the 7 goes there, 9 goes there, 8 goes there, and here again, because the 7 is fairly large, it doesn't move very far. Okay, we don't do many comparisons. I compare the 7 to the 6, I find out it doesn't go before it, and that means the 7 never gets compared to the 5, the 4, the 3, or the 2. Okay? And that's the real advantage of the insertion sort. When things are close to where they're supposed to be, you do very few comparisons with them. And in fact, the optimal for an insertion sort, if you have data that is almost sorted, if it's close to sorted, it turns out that the insertion sort is remarkably efficient. The entire thing, both comparisons and memory moves, will be order n. It will only do roughly n comparisons and roughly n memory moves. So for the 1, now of course the 1 was at the exact opposite end of where it needed to be, so we have to move everything down. We do our comparisons all the way down. We get to the front, and then we have to stop. So that's what the insertion sort looks like when we're kind of acting it out. Now we want to go look at it in code. So we go back to our sorts, and I want to write def insertion sort takes our array, which is an array of double. I have an outer loop, just as with the other sorts, and this outer loop is going to go from 1 until arr.length. So whereas the other ones went from 0 until length minus 1, this one goes from 1 to length because it is the element that I am going to push forward in there. Okay. And as we saw when I was acting this out, the first thing that I do here is I make a temporary variable, tmp equals array sub I. So I take the thing at the ith index and I copy it into my temporary variable. That way I can just push elements down and I don't have to do complete swaps. Now, the next thing I need is I need another loop, but I'm not going to use a for loop. And the reason I'm not going to use a for loop is because this particular loop needs to stop possibly shy of 0. So if I were to write a for loop, I could have a for loop that goes from I down to 0, but then it would always go to 0. And the advantage of the insertion sort is I don't always have to go that far. So instead, I'm going to start by making a j var, and then I'm going to have a while loop. So I want to keep going while j is greater than j is greater than -1, and the value that I'm looking at, so arr sub j, happens to be greater than my temp. Okay. These are my two conditions when I would stop. Either I got all the way to the beginning, so if j kind of fell off the beginning, then I wouldn't. Trying to think. We'll check for our off by ones here in just a bit, and that's one of the things. While the insertion sort winds up being almost as short as bubble sort, the logic in it is a bit more complex, and so definitely the testing is going to be significant to us here. Okay, what happens inside of here? Well, I know that the arr sub j is greater than temp, so I simply set arr sub j plus 1 equal to arr sub j. I shift the jth item back 1 in the array, and then, because this is a while loop, do not forget to increment I. Otherwise this will be an infinite while loop and it will just sit there and spin around forever and ever. Once we're done with all of that, we want to copy arr sub j plus 1. Oh, this should be a minus, I'm sorry. Subtract from j because we are going to a low bound, not an upper bound, equals temp. I could surround that inside of an if, but the reality is it's a single assignment, and for an array of doubles, doing the conditional on the if would probably make it run slower. You could do a test, but in this case it saves me typing just to not bother to put the if and to always copy it there, even if it happens that j didn't move, and so j plus 1 is equal to I, and we copy the thing right back to where it started from. So let's see if this works. Switch our min sort to an insertion sort. And I have to admit, there are chances that this doesn't work, but actually it looks like it did. 0.008, 0.09, 0.1, 0.12, 19, blah, 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 all the way down, 0.71, 0.899. Okay, so this is our insertion sort. We have now gone through a bubble sort, which was very easy to write. The logic is very simple and straightforward. but it's somewhat inefficient, and it's definitely not something you would ever do by hand. To our min sort, which actually is something you probably would do by hand, especially if you had items that take a long time to move around, something like cars in a parking lot. And the insertion sort was our most recent sort. The insertion sort is actually, it turns out, unless the things are hard to move around, if things are hard to move around, the min sort is our ideal. But if they're not hard to move around, or if they are in somewhat close to sorted order, the insertion sort winds up being the best of all three, because because this while loop allows it to not do as many comparisons. The min sort and the bubble sort always do the same number of comparisons. It's basically n squared divided by 2. They always do that. The insertion sort could actually only do n minus 1 comparisons, assuming that the array was already in order. And if it's only slightly out of order, it won't do much more than that. So that's it for this sort. We'll talk about how we could be a little bit more robust in our test.